Hey guys, welcome to my channel. In this video, we're going to talk about Faster RCNN FPN V2. Okay, so let's begin. So RCNN was first released in 2013. Then we got Faster RCNN, which was released in 2015. Then the Faster RCNN was released in 2015-16. And then finally, the latest version of Faster RCNN was released in 2023, which is called Faster RCNN V2 or FPN V2. So this is the architecture of Faster RCNN FPN V2, quite similar to the version 1. Okay. So the first model takes in an image, and at the backbone we have the ResNet 50 and the feature pyramid network. So the feature pyramid network helps in enhancing the backbone. Okay. So it does so by creating feature maps at different scales. Once we get the features, there's a region proposal network which creates different regions. So it creates anchor boxes, which in simple words are rectangles of different sizes, okay, and places it over all the features and evaluates the anchor boxes and sees whether the region contains object or not. So the regional proposal network performs a sliding window operations where it tries to identify whether there is an object or not, okay, and then it refines it and then finally creates some region proposals. So the anchor boxes which are created by the region proposal network are improved by it over time during training, okay, to fit the object in a more better way. So after creating and refining the anchor boxes, it creates the region proposals, which goes into the region of interest. Over here in the ROI, these region proposals are cropped and resized, and the original coordinates of the boxes are also preserved, so that finally when we are trying to draw the bounding boxes, we should be able to draw the bounding boxes on the original object properly, okay. And then we finally have the detection head where it analyzes the the refined bounding boxes and tries to classify what what that object is. So this is how the faster RCNN FPN V2 works in a nutshell. So what makes RCNN FPN V2 better than the original faster RCNN? So the major difference is that in this model, the pre-trained weights are much better than the original faster RCNN. The model has been trained on more dataset and for longer duration, and some better augmentation techniques have been used. Okay, and also in ResNet 50, zero initialization technique has been used for more stability. And there are some other improvements which you can see in the paper, which will be linked in the description. So you can read that paper and get to know in detail what are the improvements. Okay. So to prepare your own custom dataset, you can go to Roboflow. So over here you need to sign up and then create a new project. So over here you need to fill some details. So I'm gonna write here bus truck, for example. Here we'll select traditional. Here you need to, if you want to keep your project private, you will have to buy this subscription of this Roboflow, else you can keep it public. And then create your public project. Then over here you need to upload your data first. So here I'm gonna just select a few images. This one, this one. Okay. So here we have selected 8 images in total. So here I'm gonna select label myself. Here you need to click on start annotating. So here you need to just drag your mouse, click and drag your mouse and label the data. So here we'll write truck and done. This is our truck, okay, truck object. Then going on second one, we'll do the same. Next, here in this case, this is a bus, so we'll add bus. So now we have another class called bus. We'll do the same. Okay, so now we have labeled all our data set. And then from here you need to click add 8 images to dataset. So over here, if you want, you can split your data into train, test, validation. So for simplicity, I'm gonna just put all the 8 images in the training dataset. So after adding your images to a dataset, you need to click on versions. So over here, you need to add what kind of image augmentation or pre-processing you want to perform. Like for example, if you want to resize, you can write this over here, or if you want to orient your images, you can add this as well, or if you want to add something else over here, you can do it. So you can see there are many other operations over here, like turning your image into grayscale or doing some other kind of stuff. So for now I'm gonna remove this. Okay, and then click on continue. What kind of augmentation you want to perform? So there are different types of augmentation, like flipping, rotating to 90 degrees, cropping your images, etc. You can go through all of this. Okay, altering the hue, saturation, brightness, blurring your image, etc. So if you want, you can add any of these operations if needed, or if you want, you can also augment your images using PyTorch as well. So I've already made a video on how to augment images using PyTorch, so you can check out that as well if you want. So I'm gonna leave this as it is for now, and then we'll finally create our dataset. Okay, so now we have our images dataset ready. So we're gonna download it. I'm gonna type download zip to a computer. So I'm gonna extract all the images. So here you can see there is one folder called train, because we did not create any split. So if you create a split, then you will see multiple folders like train, test, validation, etc. Okay, so here you can see all these images over here. Okay, and the annotations are in this file. So here you can see there are four dimensional information: xmin, ymin, xmax, and ymax. Okay, here we have the class, what object it is, the name of the image, and the width and height of all the each of the images. Okay, so this is how you create your own custom dataset. So first we'll import a few libraries. So we'll be using NumPy for reading the arrays, pandas for reading the CSV file where we have our annotation details. We'll be using Torch and OpenCV for drawing bounding boxes mostly. Below, because the transforms library of PyTorch uses this underneath, so we'll be using this as well. matplotlib for showing a plot, and these are some of the functions which we'll be using from PyTorch and TorchVision, which I'll be explaining you later. So basically this is a data set having bus and trucks. So this is our CSV file. So I'll show you how this looks like. So this is how it looks like. Here we have the name of the images, the class names, and the bounding box information. Okay. So these are the only columns which we'll be using. Rest of the columns are not important to us. Okay. And then in this images folder we have all our images of bus and trucks. So let's execute this. So this is our output. So before building the model, we'll first explore the CSV file and the images in the folder and try to see how we can plot the bounding boxes with the information given in it, just to see how things work. Before starting to writing the code for our model and fine tuning it, we'll first explore the CSV file and the images and see how we can plot the bounding boxes from the CSV file, from the details given in the CSV file, just to make sure things are working fine. And then we'll proceed to the part where we'll retrain the model. So now in order to access the single row, we'll write row equals to data frame of iloc. So this will access this row. Okay, 0 1 2 3 4. Then we'll access the image name by writing image equals to row of image id. Then we'll try to read this image. So we'll first put the folder location. Since this does not have the folder location, it only has the name of the image without its extension. So the extension of all these images are .jpg. So I'm gonna write image plus .jpg and then write os.part.join bus truck slash images. Okay. Then we'll write cv2.cvt color, convert this into RGB. Since we'll be using matplotlib, then we'll get its height, width and channel. Since we'll be needing the height and the width variables, so we are just saving it in advance. So we get this. Okay, this is the height and this is the width, and these are the channels. Next we'll create a variable called boxes, where we'll store the xmin, ymin, xmax and ymax values. Okay, and then we'll convert it into float 32. This is because PyTorch by default uses float 32, okay, for its floating point values. Then we'll convert the numpy array into torch by using torch.fromNumpy, and then we'll print it. So this is what we get. After that we'll be using cv2.rectangle. So over here we have to write the top left part of a bounding box. Okay, we generally write the leftmost point as it is, but since the value that we have is a normalized value, we'll be multiplying the x part with the width and the height part, okay, y with height. Okay, so we'll write int of boxes of 0 into width and then boxes of 1 into height, and then similarly we'll write boxes of 2 into width, boxes of 3 into height, and then here we'll define the color that we want, and then the thickness of the rectangle. Next we'll try to show the image using plt.imshow and plt.show. plt.axis of will hide the axis. So we have successfully plotted the bounding box over our object of interest. So now that we know how to plot the bounding box from the CSV file on our image, we can now proceed towards writing the code for fine-tuning our model. So next we'll define a variable weights. Weights contains the default weights of Faster RCNN Resident 50 V2. Okay. So we'll be using these weights on calling a model. And then after that we'll perform some transforms operation. So basically transforms or to tensor, converts all the pixel values between 0 and 255 to 0 and 1, and converts the height width channel into channel width height format. Okay. Then we'll define our labels. So bus will take value of 1, truck will take value of 2. So in faster RCNN, the zeroth class is reserved for background class. Okay. Zeroth class is a background class. And then after that, we'll define a class called dataset images, wherein we'll call the dataset function. So we'll be using this class for constructing our dataset. So here we'll define the init where we'll call our data frame, and we'll keep the default transformation as none. So now if you want to perform more transformation, you can perform transformation like resizing and flipping, etc. So I have already made a video on data augmentation. If you want, you can refer that for performing data augmentation. But for the sake of simplicity, I'm not performing any augmentation. Okay. So your self of df will be df, self of transform will be transform this, and then we'll define a unique images variable. Okay, so in this case we'll be taking all the images and we'll only consider the unique images. So in our dataset there are images wherein there are multiple objects in same image. Okay, hence there are a lot of images which are repeated, okay, which are present on multiple rows, and in each row one object has been tagged. So let's say there are two objects in one image, so there are two rows for that image. In one row there are bounding boxes information of one object, and then in the other row there are bounding box information of the other object. So hence we'll be taking unique images. Then after that we'll define a function called len, where we'll be returning the length of the unique images. Okay. So again we are using these unique images variable because we don't want to detect only one object in one image, right? We want to detect multiple objects in an image if they are present. So we won't be calling this len directly. This will be internally used by the data loader and the data set. Okay. So after that we'll be defining our get item function. Well, we'll write image id is equal to self of unique images of ix. So here ix stands for any integer, okay, 0 to whatever is the count of our unique images, and then we'll try to open it using Python imaging library, and then we'll make sure that it is in RGB format. Okay, and then we'll convert it into RGB format just to maintain consistency, and then we'll try to get the width and height of our image. Now if we want to perform transformation, then we'll pass this transforms argument, and then if transform argument is present, then it will perform some transformation. Then we'll find all the particular rows where the image id is equal to this particular image id. So let's say for example if we are on index 0, okay, then in this case image id is this. Okay, now like I've said before, there could be multiple rows for a same image if there are multiple objects present in that image. Okay, so hence we want all the rows with a particular image id at a time. So we'll put that value in the variable called rows. Okay, and then we'll define a variable called boxes and then labels, and then we'll use iter rows. So let's say for a particular image there are two rows, so we'll loop over it. So we'll let box equals to r of xmin, ymin, xmax, ymax dot values. So we'll convert it into array by using dot values. Then we'll convert it into float 32 just like we did it above. Okay, and then we'll multiply the x value with the width and the y value with the height. So this is xmin, this is ymin, this is xmax, ymax. Okay, and then we'll convert it into integers, and then we will append it in the boxes, list. So basically this will contain the bounding boxes of all the objects in an image. Okay, name, and then similarly we'll also try to get the class name by using data label of r of label name, and then we will append it in our labels list. Then we let boxes equals to torch.tensor boxes. We'll convert this into torch tensor. Okay, we'll keep the data type as float32, and the labels will be of type integer. Then we'll create a dictionary target, put the boxes in the boxes key and labels in the labels key, and then return the image and the target. So basically what we are trying to do over here is we'll find the unique image. Okay, we'll try to read its location. We'll read that image using Python imaging library converted into RGB for maintaining consistency. And once we have our image, we'll try to transform it. Okay, so that's how we get our image over here. And then in order to get the target, we take a particular image ID, try to get all the rows of that particular image ID. Image ID was already defined over here. So for this index location, let's say 0, what is the image ID? So it will get all the rows of that image ID. Then we will define our boxes and labels in an empty list, and then we will iterate over it using iter rows. Then we will try to get the individual box and the xmin and the ymin and the class name and everything. Okay, and then at the end we will just append it. Okay, and then we will try to convert the data type. Make sure the boxes, bounding boxes are of type float32, and then labels of type integer. Then we will define our target, because this is how the faster RCNN expects the target to be. Okay, so there are more than 10,000 images, so I'll be taking around 3,000 images for training and 600 images for testing. Okay, and then after that I will call this function datasets images and call this as train dataset and test dataset, and then pass these two arguments. Okay, then we will apply this collate function. So basically what this function will do this, so let's say there is a list of tuples. Okay, let's say 1 comma 2 and 1 comma 2. Okay, so it will convert this into 1 comma 1 and 2 comma 2. Okay, so here what we are trying to do is we are trying to get a separate list of images and separate list of targets. So earlier we are having a pair of image and targets, but now in the data loader we'll be sending images and targets separately. Okay, because that's how it works. So we let data loader train data set number of workers 4, batch size 4. If you have a better GPU, you can increase the batch size. We'll use shuffle true for training data set. We won't be using shuffle for test. And then collate function equals to collate function. After that, we'll define a variable called device. So it will be equals to CUDA if toy.CUDA is available. That is if GPU is configured on a system. Okay, it will use CUDA as a device, else it will fall back to CPU. Now if you want to know how you can configure your PyTorch and GPU, you can watch this. Now if you want to cross verify whether your PyTorch is detecting your device, you can write toy.CUDA.device name, and it will show the device that you have on your system. Okay, then after that we will load the pre-trained model from PyTorch. So we write models.detection.faster RCNN resident 50 FPN v2. Okay, weights equals to weights. So if you don't write this, it means that it will load this model without any weights, without any pre-trained weights. After that, we will import this faster RCNN predictor. Then we will try to access its in features, okay, of this final layer CLS score, and then over there we'll try to insert the number of classes. So we'll keep the in features as it is, but we will just change the number of classes to 3. So 0 will be the background class. The other two classes are bus and truck in our case. So if you have, let's say, 5 different classes, so here the number of classes would be 6, including the background class. So here we'll try to freeze the backbone. So we'll add model.background parameters, and we'll make requires grad equals to false. It means that these, you know, the layers in the backbone won't be trained during the transfer learning phase. Okay. Then we'll add model.toDevice. Since we want to use GPU, we'll write this line model.toDevice, and then we'll print the model. So if you want, you can see this is the architecture. So it's quite lengthy. So here you can see the output features for bounding box is 12. Okay, this is because box has 4 corners, right? So 4 threes are 12. So that's why here it is 12. And you don't have to separately write this, okay? It will automatically calculate this b box spirit. So this function will automatically calculate this, okay? Then we'll try to get the parameters for which there is required grad. Okay, requires grad is true. Then we'll try to get the Adam optimizer. We'll set the learning rate, weight decay, and then we'll start the training. Okay. So here I had trained only for 4 epochs because I have only 6 GB of GPU. So it was training quite slow. So here I've created 2 lists for train and test loss. Here we'll put the model in the training mode. Then we'll loop over our train data loader. Here we'll mention the batch count optionally. Then we'll write x comma y equals to batch. So here this is our input image. This is the target dictionary. And here we'll try to extract all images and put it in a list. Okay. Since it is a batch of size 4. Okay. And here we'll try to create our target dictionary. Okay. Of boxes and labels. Okay. Then we'll try to get the loss. And here we'll try to sum it up. Okay. So this is the loss for a particular batch. Then we'll try to accumulate all the batches in a particular epoch and then append it, okay, in the total loss. Then we'll do the same for the test data loader as well. So here we won't be putting this in the evaluation mode because it won't give us the loss dictionary, okay. So we'll keep it in the training mode itself and just collect the loss for validation just to see how it is performing. And this is optional. If you want, you can skip the test data loader, but I have kept it for reference. And here you have to do the same thing, okay. And here I am printing the loss, okay, for train and test. So here if you see, this is our train loss and this is our test loss. And as you can see, I have set the epoch size just to 4, and it still took a lot of time on my system. So of course you can train it for more number of epochs, like 20 at least, and make it much better, okay. And then you have to save it using these commands: toy.save model.stateDict. So this will only save the weights, okay. Now we'll try to perform some testing and see how it is performing. So you have to first import all these things. Here we'll try to again load the model, but this time we won't be adding weights, okay. Here again we'll write device equals to CUDA or else CPU. Then again we'll write the same thing over here, and here this line will also be same just like our previous code. Then we write model.toDevice. We'll try to load our model using toy.load. Weights only equals to true. Then model.load state dict. So earlier we had done toy.save model.state dict. Okay, so here we'll first load it with torch and then model.load state dict. We had defined the architecture over here and we are just loading the weights. So if it is successful, it will show you something, a message like this. Okay, and if you're getting any error, it means that there is some mismatch in the weights and the architecture. Then we'll put the model in the evaluation mode. We'll try to, load a random image, convert it into RGB, perform this transform to tensor. Okay, apply this transform on the image. We'll try to unsqueeze it. So this is the batch dimension. These are the three channels since it is an RGB image. This is the height and this is the width. Okay. Then after that we'll read this image. Okay, the same image over here. We'll try to read this image with CV2 and then use the label map which we had used before in our older code. Then we'll write toy.inference mode. Okay, so before evaluating a model you need to remember two things. First is to call model.eval and then toy.inference mode. Okay, so we are applying these two things because we don't want to do any gradient calculation. Okay, so and these two lines are important. Then we let output equals to model of image tensor. Here we'll set a threshold of 0.45. Here we write boxes. Here we'll define the variable boxes, labels and scores. First we'll create a mask. Keep equals to scores greater than threshold. Okay. So we are using this mask because we want only the boxes and the labels which have a score greater than this. So here we write boxes equals to boxes of keep. Similarly, we'll do the same thing with labels and scores. So this will automatically filter out all the boxes, labels and scores which have a score less than 0.45. So we are trying to detect as many objects that we find in an image. So hence we are applying a for loop over here since we have multiple bounding boxes. So we are getting the length of the bounding boxes, and then here we will try to create a rectangle and then put a text of labels. Here don't forget to convert the image into RGB since OpenCV converts images into BGR. You want to know the difference between RGB and BGR, I have made another video. You can watch that. It's a very old video, so please don't mind the quality. So here you can see we have identified the two trucks. So I hope you found my video helpful. Don't forget to subscribe. Thank you very much.